simplify further, because we said the interaction part would have this dipole, the excitation value of the atomic dipole dotted with this G of the field. Let me turn this whole thing. And actually this is only dependent on the position of the atom. Okay. So let me turn this whole thing into some lambda, and we're not going to worry about it for now. Okay. So let me call that lambda, which is not the wavelength. Okay. This is just a strength of the measure of the strength of the coupling is equal to the maybe we should even attach the E. Okay. E times D dotted is G. Okay. So this is the lambda. And of course, if we're considering multiple wave numbers, the lambda is addressed by multiple wave numbers. Okay. So that's it. And by writing that down, we can turn the interaction Hamiltonian method is equal to lambda K sigma plus and throwing away the time dependencies by saying that we're writing things in the Schrodinger picture. This is so this is the quantized interaction Hamiltonian. All right. Any questions? So. Now the fully quantized atom this is basically write down the Hamiltonian for the atom, which in the two-level representation is very simple. Right? We can just write E of the energy of the excited state plus energy of the ground state. Right, that's the atom. And then the field, still we have a summation over K. Okay. And it's just going to be the energy of the different fields. H bar omega K times the number operator of the field. Okay. So this is the field part. And of course I've thrown away the, what's missing here. When we quantize the field, there's a 0-point energy. I'm throwing that away because that just amounts to changing the reference point of the zero of energy. Right? And then there's that interaction part, which is summation over K, lambda K, sigma plus K. So this is the fully quantized Hamiltonian. I can simplify this further by saying, well, for the atoms, we've drawn the diagram like this. Now, what if I put the zero of energy at the midpoint over here? I'm going to say that this is the energy equals to zero reference point for the atom. Then, and I know that the transition frequency is h bar omega naught, as I have defined previously. Right? So with this setup, then the energy of the excited state is just 1/2 h bar omega naught. And the energy of the ground state is minus 1/2 h bar omega naught. Right? Right? Okay, so if I take this common factor out, I get this subtracting this. If you think about it, this is like 1 minus 1, 0, 0. And this is what? Sigma 3. Okay. So I'm going to replace this with 1/2 h bar omega naught. So now we've done this part, compensation and the rotating wave approximation. Okay. So now this atom is coupled to a bunch of different wave numbers, so a bunch of field modes. Okay. And you can study, let's say that we have an atom. You study an atom, okay, that's sitting in some big volume which have done the compensation. Okay, and from this Hamiltonian, you can study things like spontaneous emission and stuff, because now the field is quantized. So the atom is coupled to a quantized field, which includes the effect of the vacuum, quantum vacuum. And by coupling to the quantum vacuum, you get this spontaneous emission thing. Okay. You could study that, but let's not worry about this problem right now. Okay.
Can you explain why you draw the 0-point energy part?
Because, okay, so throwing out the 0-point energy part doesn't mean that we are no longer coupling to the quantum vacuum. Why is that? Because the information of the quantum vacuum is encoded here in how they commute with each other. The actual 0-point energy just amounts to, in the Hamiltonian, it just amounts to a change in the zero of energy. Okay. Suppose the 0-point energy had a definite value. Suppose it did. Then by subtracting it, I just add a phase factor to everything. That doesn't mean we're not coupling to the 0-point energy here. Correct? Yeah. Does that explain, guys? Okay, so remember that the coupling to the 0-point energy, the coupling to the quantum vacuum is really happening in how these operators are going to commute with each other, because the statistics is encoded there. Okay. It's not because it's not actually including the quantum vacuum energy part. So yeah, that was a point I needed to clarify. Now let's consider even simpler problem where the atom is just coupled to a single mole field, just one. Okay, and how is this possible? Okay. How is this possible? How can you make a single mole field? And what's actually happening is this. Okay, so I need to tell you guys how the regime of relevance of this James Cummings model. So if I were to plot out the transition frequency and the atomic dipole moment is these things. Okay. Roughly, if I were to plot this out, then it's going to be a bunch of peaks, right, corresponding to the allowed transitions of the atom. Okay. Now let's center it around one peak, and because of Fermi golden rule, okay, there's going to be some spread because of the energy time uncertainty. Okay. I shouldn't say it's because of the Fermi golden rule. Okay, so roughly it's going to look like this with some spread. Okay, some spread in the delta omega. Okay. So now I can make a cavity. Okay, I make a cavity like this. Mirrors on two sides. Okay. And then the field are quantized inside of the cavity like this. Okay. And I need a curved mirror because I want the field to be stable. But that actually doesn't concern us here. Okay. So the k's are quantized in the z direction. Let me call this the z direction. The k's are quantized, and therefore the omegas are quantized. Right? Okay, so for this one, depending on the quality factor, of the cavity, then the moles are like this. They're roughly equally spaced. And what's their spacing? I'm going to tell you this is, the length over here is L. 2 pi over L, right? 2 pi over L times C, yeah, because I'm writing omega, that's good. Okay. So imagine, so this is just the mole, so I don't know what to write here. This probably doesn't have any meaning. And so now imagine if I were to overlap these two, and by choosing this the length here, okay, I can choose such that the atom is effectively only coupled to one mole like this, okay, while the next mole might be way over here and here, okay. So this is how we are able to couple the atom to exactly one mole. But notice that this coupling means that the atom can make a transition to this mole. It doesn't mean that the atoms, okay, all these moles are still coupled, are going to be there in the cavity, okay, but the atom just doesn't have this rotating wave approximation with it. The atom still reacts to those moles, and we'll see how it reacts in maybe on Thursday. Okay, but right now, it is possible in this regime with a possible transition. It only couples to one mole. Okay. So that's how we're able to couple it to one mole. Experimentally, it can be done. And maybe if we have time, we can talk about some experiments in this with this setup. Well, I was saying, forget about all these summations. Let's just pick out one mole. Okay. And by picking out one mole, we arrive at I'm going to just denote it by omega and drop the k, because there's no ambiguity anymore. And this is the James-Cummings model. So the James-Cummings model is very popular because it's quite simple. But remember that there are a bunch of approximations that we did in arriving at the James-Cummings model, and that limits its applicability to very general problems. Remember we did, what are the approximations that we used? First there was a dipole approximation which allowed us to write the E dot R thing, right? And then there's the rotating wave approximation, which means that we're thinking about essentially R resonance or near resonance physics. And nothing else, right? Just these two approximations. And provided you have a cavity that allows you to just couple it to a single mole. Okay. So now we turn to solving this Hamiltonian. Okay. So to solve this Hamiltonian, we use a mechanism or another often used technique called the interaction picture. So before I do that, let me rewrite something over here. So in writing down a Hamiltonian, we can solve it by extracting out. Let's extract out what's constant throughout the motion. So let's extract the constant of motion from this Hamiltonian. And we assume that this cavity has perfectly reflecting mirrors, or that over the time in which the characteristic time in which these atom field interactions happen, there's no chance of the photon escaping the cavity. So basically, the cavity has a very high Q, very high quality factor. Okay, in that case, the constant of motion is first of all, the number of photons is not conserved. Because the atom can absorb or give off a photon. But if I count the number of photons and the excited state of the atom, then that number is conserved. So this is called the number of excitations, which I denote as NE. This is a constant of motion. And this is written as, in terms of operators, is E. This is what? 1, 2, something like this, right? Okay. And then plus basically the number operator for the photon field. This one. Okay, so this is conserved. What else is conserved? Think about a simple thing. Something else must be conserved. The number of electrons. There's only one atom there. So the atom can either be in the excited or the ground or a superposition of them. But if it were in a superposition, probability must be conserved. Right? So let me write. So this is the number of excitations. I'm going to write number of electrons. Okay. And this is probably a atom. Which is this. So this is these two are the constants of motion here, right? Right. So these two things, constants of motion just gives you overall phase factor in the time evolution. Right? So let me extract them out, and then we're going to be left with the important part that gives you the dynamical effects. Okay. So how can I extract these out? Well, I know that sigma 3 is EE minus GG. So, and then we have this over here. So let me try to extract this constant of motion from this term, okay, by supplying it with this. So this is again just some boring algebra. That accounts for this term. Okay. And then we have a plus 1 term H bar. And do I need to worry about these things? They clearly will give me the dynamical effect, because they're describing things like the atom transitioning. So I don't need to worry about this part. I just work with this. Okay. So now, okay, let me combine these two terms. And from here, I'm going to extract this constant of motion, and that amounts to just subtracting the factor related to the ground state. So let me switch this around, turn it into a plus sign. Okay. So switching this around, we get a plus. This one over minus this. Okay. We're going to turn this into this constant of motion, NE over here, and then subtract this multiplied by the ground state. Okay, you have a subtraction of this, and then combined with this factor, and that gives you basically minus H bar maybe not minus H bar maybe. Correct? Okay. So now we find that this is interesting. Let me turn this term into H bar delta, where this delta term is related to the detuning related to where I ground over here. Suppose that the atomic transition is centered around omega. The latter is related to this omega, okay, and the difference here, which I'm calling the delta. So this is a detuning factor. Okay. So now from this part, the non-interacting part, consisting of the free atom and the free field, we extract out these constants of motion plus something that resets the energy of the ground state. Okay. So now I can write the Hamiltonian as. Okay. So since all these parts consist of constants of motion, let me write it with maybe H naught. And it's no longer an operator because these are constants of motion. They will just come out to be numbers. Okay. Minus H bar delta correct? So I'm going to call this part the new interaction part. And this is clearly an operator. Are there any questions? This part is just algebra. But it tells you something interesting, and that's that by copying to the mode in the cavity, we effectively have a energy shift in the ground state when we consider the interaction. But actually, this is non-existent because if I were to combine these terms, I still get this, right? The ground state by the atom itself is still going to be minus h bar omega naught. Okay? But this tells you that when you consider the atom and the field as a whole, then this ground state, which is clearly no longer going to be an eigenstate, gets shifted in energy. Okay? And we're going to later find out what are the eigenstate energies in this James Cumming set. Okay. Are there any questions? Okay. Yeah.
Can we talk more about it? Because if I remember, I'm trying to learn come up with names.
Okay. Can you ask that again?
Detuning.
Oh, the detuning. I mean, there's not much to talk about it now. It just comes out as a factor. But let's later, maybe on Thursday, when we consider the detuning is an off-resonance thing. Now let's think about what physics is related to the amount of detuning. It turns out that some effects, when you consider non-resonance physics, some effects are related to the strength of this detuning. We can talk about that on Thursday. Maybe that's what you're looking for. Today I'm going to solve this for you in the case where the detuning is 0, so in an exactly resonant case. Okay. So exactly resonant. We just have this term there. Okay. Now I need to introduce the interaction picture, okay, which is we've done the Schrodinger picture and the Heisenberg picture, which is like this. How do I link between these two pictures? Basically, I'm saying that the expectation value of the observables should agree across different pictures. So in the Schrodinger picture, we have a Schrodinger equation with some state that's a function of time is equal to the Hamiltonian acting on that state. So Hamiltonian generates the time evolution for the state. That's the Schrodinger case. Okay, and now I can formally write e to the I as set T, right? Correct. Okay. Now, for some operator observable that which doesn't move in the Schrodinger picture, I will write down some operator, maybe A operator like this, not the vector potential, just an operator. The expectation value of A as a function of time is equal to, in the Schrodinger picture, well, the state at time t, sandwiching this, okay, which I could very well write. I could extract out the time evolution. And then now, if I group these things together, I'm in the Heisenberg picture. So this is the Schrodinger picture. This is the Heisenberg picture. Now there's yet another way to do this, which is specific to problems where you have a free Hamiltonian and an interacting Hamiltonian. Okay. So we still make a link over here. So this is still going to be equal to psi of t. But now let me sandwich something in between here and here, which is I'm going to write h naught t Why are we doing this? So now I can define a time-dependent operator that's this, and a new state, which I will call psi tilde of t. And over here, notice that this is just a graph of psi tilde. So this is where?
H9.
Oh yeah, I have H0. So I'm only, so to do this, you need to extract out this bit. It's only good when you have this distinction between a free Hamiltonian and the interacting part.
So your third line says that psi t is defined to be that, so the exponential seems to cancel in the second last line.
It depends, because this psi of t in the Schrodinger picture will consist of the total Hamiltonian, right?
The h that you have is not the total one?
Yeah, the h I have is the total one, but I've written h naught here. Yeah, so, and sometimes you can have a cancellation. Basically, this part, this minus I h naught, this.
Yes, we are not to see your h dot, I suppose.
Sorry. Yeah, okay, I guess. Oh, wait, I made a mistake here. There should be a minus sign here, first of all. Okay, so it should be a plus sign. And then with that kind of definition, I guess I would want this. So sorry about that. Made a mistake here. So imagine, let me explain this in more detail. So in the Schrodinger picture, the state evolves using the total Hamiltonian, from the initial state to a state at time t. And the evolution is generated by the total Hamiltonian. In the Heisenberg picture, everything is the same, except that we're going to attach time evolution to the operator. Okay? And the operator evolves. And you basically take the initial state, and to find the expectation value, you find the operator that evolved to that state and to that time, and then you take this expectation value. In the interaction picture, first thing you do is you separate the Hamiltonian into a H0 part, which is roughly, in some cases it can be consisting of constants of motion, and the interaction part, okay? And we still start with this defining equation, which is true in any picture, okay? With the psi of t written in the Schrodinger picture, and the time-independent gain. So although this is true in any picture, I've chosen to write this in the Schrodinger picture explicitly. And then I'm going to attach some phase factors. And I'm going to basically insert two identities here and there. And the way I write the identity is by breaking it. So the identity, in this case, is broken into a unitary operator times its Hermitian endpoint. And I know that for a Hamiltonian consisting of H0, if I exponentiate this, it's going to be turned into a unitary operator. So inserting this is just the identity. But afterwards, I'm going to group different terms together. I'm going to group these into a new operator. Maybe I should write it as well, okay? But it gets clumsy. So this is a new operator that evolves with the H0 part, okay? And then this is a new state, okay, that evolves with this, multiplying the state in the Schrodinger picture, okay? And if I were to relate this state to the initial value of the state, then I would get e to the I something like this. And depending on whether the H0, okay, this part, commutes with the interaction part. If they do commute, I can then these things just become a simple addition. Okay, just multiplying the exponentials just becomes adding the exponents. And why is that? Because if two operators commute, they share a common eigenvector set, a common set of eigenvectors, and I could expand everything onto that eigenvector set, and then it becomes an equation dealing with eigenvalues, and I know those eigenvalues turn these things into numbers. And for numbers, certainly I can combine the exponents. But that only happens when they do commute. In our case, they do commute. Why is that? Because anything that's happening should certainly commute with constants of motion, right? They're constants, so they're just numbers. Of course they commute. In this case, they do commute. And what you find is that after this cancellation, right, you basically find the interaction Hamiltonian up here. Okay, correct? Because the H0 part has been cancelled. And this is like writing things in a new kind, in a special kind of Schrodinger picture, where you have psi tilde t is equal to this. The interaction is caused, the time evolution is just caused by the interaction part of the Hamiltonian. So now I can write down a Schrodinger equation with just the interaction part. Okay? So this thing is certainly equivalent to I h bar d gt psi of t is equal to h interactions. Right? Okay. So this gives you one way to do the interaction picture. This is just one way. Okay. There are more complicated ways when we need to think about, well, when I cannot do this, when they don't compute. And there are other formalisms for the interaction picture. But today, with our simple picture, we just need this. So this just amounts to writing down the Schrodinger equation, forgetting about the constants of motion, which just gives you, as I said, gives you overall phase factors that's not needed. Overall phase factors that wouldn't show up if I were considering expectation values like this. So now I just write down the Schrodinger equation. It's just a interaction Hamiltonian. Okay. And the exactly resonant case, I can even forget about this part. Just this. So do I have enough time to solve it? Okay, I guess maybe there's not enough time left. Let me just write down the problem that we get in the end. So in the interaction picture, I get a different set of Schrodinger equation corresponding to, once again, a change in the phase. So these switching between pictures is just like you attach time dependence or you give a phase shift or something. And it's all very, it's quite simple. Okay. So now what we can do is let's think about what are the possible states in the interaction. So because there are some conserved numbers, we know that the dynamics is only going to happen between two possible states. If the number of photons was initially a fixed thing, okay. Suppose the atom started with the atom in the excited state and the number of photons being n. Okay, suppose these were known. Then the only possible state that it transits